Sometimes I forget to hit that button and then I don't have a recording, but okay. So it looks like what we're doing here is looking at the relationship between linear ratio, area ratio, and volume ratio, correct?
Yeah.
That's what all of this is about. How are you with this stuff?
Well, with this page, he kind of just gave it to us on Friday and didn't even like explain it.
Okay.
So
In that
that's where I
case,
am.
let me do something other than dive directly into problem one.
Okay.
Let's talk about these three relationships. If I have a square, hold on a second. Yeah, okay. And that square is 3 inches on each side. And I have another square that is twice that, 6 inches on each side. Notice that the linear, here, let me write it over here. The linear ratio is 2 to 1. And
Mhm.
I always prefer doing big to little. And I know that some of the teachers at Chatfield do little to big.
Yeah, that's what he does.
He does little to big, then I'll
Yeah.
switch to little to big. The reason
Okay.
I don't like little to big is because it introduces fractions unnecessarily. Uh,
Yeah.
but that's okay. The linear ratio is 1 to 2. But what is the area ratio? The area of that is 9. The area of that is 36. So the area ratio is what?
It'd be 9 to 36, right?
It'd be 1,
And
yeah, 9 to 36, which is 1 to 4,
yeah.
which is the square of the linear ratio.
Okay.
And now let's take it to a box, three-dimensional, that is 6 on each side. So the linear ratio between this square and this box is still 1 to 2, but the area ratio is 1 to 4. And what's the volume of this box?
Um, 6, right? Or 3. No, 6.
It's 6 times 6 times 6, which is 216. So the volume ratio is 9 to 216, which is 8 to 1. It is the linear ratio cubed.
Okay.
So when you go from linear ratio to area ratio, you square it. When you go from linear ratio to volume ratio, you cube it.
Okay.
And perhaps, I don't know why I went to 6. I should have done this. I should have drawn a square, 3 by 3, and no, this is the way to explain it. Yeah, no, this is good. So this is very important. Once you figure out, now notice why big to little works a little bit better. Because big to little, this becomes 2 to 1, this becomes 4 to 1, this becomes 8 to 1. So 2 squared is 4, 2 cubed is, with fractions, it becomes a little harder to see it. But 1/2 squared is 1/4, and 1/2 cubed is 1/8. With me?
Yeah.
Okay,
Yeah, I get it.
let's go tackle these problems.
Okay.
Now, of course, they give us a hard one to start. What's the linear ratio? They're giving us the volume ratio. In other words, they're giving us, is this the notation your teacher uses?
I don't think so.
L sub r, A sub r, and V sub r? Well, I don't know what your teacher uses, but that's what I'm calling the volume ratio. The volume
Because he
ratio,
knows like the LAV thing.
LAV?
Yeah, like we set it out in like a table.
I'm not sure what you mean by LAV. Oh, yeah, L is the linear ratio, A is the area ratio, V is the volume ratio. Okay, so I'll just use L, A, and R.
Okay.
I put a little sub R there because it's a ratio. It's always a ratio. Even if it's 2, it's 2 to 1. Okay? So that's the volume ratio. Tell me what the linear ratio is.
Linear. Because it's squaring it, right?
Cube. You need
For
to
linear?
take the cube root to get back to linear.
Okay.
Remember, if the linear ratio is A, then the area ratio, is X, then the area ratio is X squared, and the volume ratio is X cubed. Okay? So to get from volume back to linear, you got to take the cube root. So what's the linear? What's the cube root of A cubed over B cubed?
Well, I don't know because how you do that without numbers? Is it just A squared B squared?
Yeah. In other words, whenever these exponents are the same as the root, it's like the cube root of A cubed is A, always, no matter what A is. Think about it. The cube root of 2 cubed. 2 cubed is 8. The cube root of 8 is 2. So it's always that number right there. Okay? So the cube root of A cubed, that's why I say they started us out with a hard one. Why couldn't they have given us an easy one with numbers in it?
Yeah.
But that's okay. We can still do it. So now we got the linear ratio. Tell me the area ratio.
It would be A squared, right? B squared.
Over B squared. You got to square both. You're squaring the whole thing. This is, first of all, the same as this. They're not different. They're the same thing. Okay? This is this also. So the question says, what's the ratio of their surface areas? A squared over B squared. It's this ratio. But to do it, we had to take the cube root first, and then we had to take that answer and square it. Well, in reality, we could have taken that to the 2/3 power. In other words, we could turn 2 steps into 1 step, but it's much more understandable if you do it in 2 steps. I think you agree?
Yeah.
Yeah. In other words, no matter what they give you, sometimes they give you the volume ratio, sometimes they give you the linear ratio, sometimes they give you the area ratio. The first thing that really is useful to do is come up with the linear ratio. And then you can do the area or the volume ratio quite easily. It's when they give you the volume and they want you to go straight to area that it's a little confusing, and you have to really kind of do it in 2 steps. You have to get to the linear first. So that's actually my favorite means of doing it. You can't go wrong finding the linear ratio first. if you try to do it in one step, sometimes you can get that thing backwards. You can do 3/2 instead of 2/3, and then you get the wrong answer. So it's better to do something in 2 steps with total accuracy. So the answer to that is a squared over b squared. All right,
Okay.
now at least they give us one that has numbers in it. The ratio, and he hadn't really given you much information about any of this?
Not really, like, he just kind of gave it to us.
This is the first problems he gives you? Oh, it's criminal. Okay.
Yeah.
The ratio of the weights of 2 spherical balls is 27 to 125. What's the ratio of their diameters? All right.
So the weight is
Another super hard problem. You're taking honors geometry, or aren't you?
regular.
Just regular? Really?
Yeah.
And this is questions 1, 2, and 3 without much introduction? Okay.
Yeah.
All right. So first of all, what does that tell me? It says weights.
So that's volume,
Correct.
right?
In other words, the
So that's
ratio of the volumes is going to be the same as the ratio of the weights. It's not exactly clear that that's what it would be, but it is. Okay, as long as it's a uniform substance, like it's steel balls. Steel balls are all steel. The density of steel is the same everywhere, so whatever the ratio of their weights is, that's the ratio of their volumes. So the volume ratio is 27 to 125. And just so you notice that each of those numbers is a perfect cube number. So what's the next step?
So we need to find the area and the length, right?
Yeah, but that's not the next step. The first step is always to find the linear ratio first.
Okay.
Tell me what the linear ratio is.
Would it be 9 to 5?
It's the cube root of that divided by the cube root of that. In other words, the difference between linear ratio and volume ratio is cubed. So if you want to go from volume to linear, you got to cube it. Take the cube root of it.
It would be 5 for the bottom, and then 3 for the top, yeah.
You know what's really worth knowing is squares and cubes. Perfect square numbers. You with me?
Mm-hmm.
Perfect cube numbers. It's really good to know these. In other words, it's especially in this section. In this section of geometry, more than any other place in math, you want to know your perfect square numbers and your perfect cube numbers, because they're constantly giving you problems like 27 divided by 125, and you got to take the cube root of it. And so if you know these numbers, you recognize 27 is a perfect cube number, and so is 125. That's 3 cubed, that's 5 cubed. So you can do it without a calculator, and it's quite helpful to be able to do these without a calculator.
Mm-hmm.
It just is, trust me. And you don't need to know fourths. There's nothing to the fourth power in any of these problems. It's all, everything's being either squared or cubed, which means if you're trying to get back to the linear ratio, you're either taking the square root or the cube root of a number.
Okay.
All right, let me erase those, memorize those. So you recognize, when you see 125, you know that is 5 cubed. When you see the number 27, you know that's 3 cubed.
Okay.
All right. So what is the ratio of the diameters? Is that a linear measurement, or is that an area measurement, or is that a volume measurement?
Would that be, I think it'd be linear.
Yeah, and it's all you need is what are the units going to be? Are the units going to be in inches or square inches or cubic inches? Well, if you're talking about a diameter, it's in inches, right?
Yeah.
So this is the answer, 3 to 5.
Oh, okay.
Okay? So no matter whether you're asking about area or linear, you got to find the linear ratio. That's just almost a given in all of these problems. Find the linear ratio first and then go from there.
Okay.
All right, let's take a look at 3. Okay, and they get harder. Well, Chatfield is a very demanding curriculum, for sure.
Yeah.
So let's draw a picture of a tree. And she's able to see the tip of the tree in the mirror when she stands 6 feet from the mirror, which is, whoa, okay. So when the mirror, here we have a mirror, and sometimes to understand these, you almost have to draw a picture of it.
Yeah.
That mirror is 42 feet from the base of the tree. And she is standing 6 feet from the mirror. So she's standing right there. I'm a terrible artist. That's terrible. It's not a good thing to be a bad artist either when you're a math tutor, it's helpful to be a good artist. Not so much in geometry, but when you get to calculus, it's really helpful to be able to draw three-dimensional objects. And I'm not very good at it. I apologize.
Yeah, neither am I.
Okay, do I have this? She can't be on the other side of it, right? It's got to be on this side of it. That's the only way she's going to see the tree. So it's 6 foot. Okay, in such a way that she is able to see the tip of the tree in the mirror when she stands 6 feet from the mirror. And the mirror is 42 feet from the base of the tree. How tall is the tree if her eye is 5 foot 4 inches from the ground?
Oh,
Let's draw our mirror slightly bigger so that it goes up to her eye level. And this tree is obviously bigger. And what they're saying is that her eye sees like that.
okay.
And, her eye level is at 5 foot 4 inches. So right offhand, what would you think the answer would be? And I'm almost certain that this is the answer, but it's not that simple of a problem by any means. And I'm not sure that the answer that I'm going to give you is actually the correct answer.
Okay.
No, seriously, first of all, what's the ratio of the distance of the tree from the mirror to the distance of the person to the mirror? That's a linear ratio. What is that?
Would it be 6 over 42?
Yeah, that's fine. I don't care if you do little to big. Actually, I
Okay.
hate it. But I do hate it. I think it's a terrible way to teach this stuff. I think big over little works a lot better.
Yeah, I don't know, like the whole math
Take
department
cube
at
roots of 8. If I say take the cube root of 8, you tell me 2. It might take you 10 minutes or 10 seconds to figure it out, but you get there. If I tell you take the cube root of 1/8, that's much harder to come up with 1/2. It just is counterintuitive that when you take the cube root of fractions, you get bigger. You don't get smaller, you get bigger. So taking the cube root of a fraction is much harder than taking the cube root of a whole number. But Chatfield insists upon teaching this way, so I got to adapt to it. So the relationship is 7 to 1 or 1 to 7.
Okay.
Oh, how tall do you think this tree is?
42. Ooh. Would it be,
Just give me the conception or the concept.
are we squaring it or are we,
No,
or we're not doing
this is all linear. There's no areas here. And the height of the tree is in feet. The height of the person is in feet. And everything's a distance in feet. There's no area anywhere involved here. So this is actually quite different than the first two questions.
Okay.
Okay? And I'm going to tell you why I have problems with it, but right offhand, I'm going to say the height of that tree is 7 times the height of her eyeballs. So 7 times 5 1/3 foot. That is 37 1/3 feet. That's the height of the tree.
Okay.
Okay? Because everything's linear. This is not a case of comparing linear to area or volume ratios. This is strictly linear. And obviously, notice that if she's standing back here, 42 feet from the mirror, she doesn't see the tip of the tree. Right?
Yeah, because she's.
No, there's no expansion. There's no amplifying. She sees this level of the tree right here. She sees 5 feet 4 inches.
Yeah.
And I guess here's the reason I have a little problem with this problem. I'm quite certain that this is the answer, 37 1/3 feet. Do you have answers on these, by the way?
Yeah, I can get him tomorrow. He has a little,
Okay.
he'll give it to us.
You don't have them right now?
No.
Okay. Well, that's what I'm going to say the answer is. Although I don't really like it as an answer, and I'll tell you why, and that's because there's an angle. For her to see the top of the tree, her eyeballs are not going like this. Excuse me. Sometimes I'm on erase and I don't know it. They're assuming that this takes place. She's looking dead on. Well, you don't get the top of the tree if you look dead on. You got to look a little higher In other words, there's an angle of reflection there. If she's seeing the top of the tree, then she's really seeing that. And that becomes a much, much more complicated geometry problem. And I'm not sure they intend for this to be that complicated. It's complicated enough as it is.
Yeah.
So I'm not going to spend any more time on it, but it could be that my geometry is slightly off here, because I actually think that they're assuming that she's looking directly at the mirror and she's seeing the top of the tree. And maybe that's actually true. I suppose it depends on how tall the mirror is. No, you're right. I mean, the problem is right. There's going to be a 7-to-1 amplification.
Okay.
If she's 1/7 of the distance, she's going to see the whole tree. She's going to see all 7 times her height, or her eyeball height. All right, let's go on. I'm not even sure I like that problem. Well, it doesn't teach anything about these ratios, and furthermore, it is a confusing problem, and that question as to whether there's an angle between her eye and the spot on the mirror. So let's go to number 4. This is back more to linear area and volume questions. So what are they giving us with the first sentence?
That the area is 4:9, the ratio.
Okay, the area ratio is 4:9. Again, they always use perfect square numbers. If your goal is to have to find the linear ratio, what is it?
It would be 2:3.
What's the ratio of their corresponding sides? Now, how can you tell that they're talking about the linear ratio when they say that?
Because it's the sides, like.
Well, because if you were to measure a side, you'd get inches or feet or meters. You would not get square anything, right?
Yeah.
So whatever your unit of measurement is, that tells you whether they're talking about linear ratio or area ratio or volume ratio. And even their corresponding sides are always going to be measured in a linear unit. They're not talking about a tetrahedron here, and they're not asking you about what's the ratio of the areas of their corresponding faces. That would be in square inches, so that would be an area ratio.
Okay.
Okay, but in this problem, it's strictly a linear ratio. Okay, number 5. Corresponding heights of 2 similar cylinders is. What information did they just give you?
That it's a length, because the height is the length.
So what are they giving you?
That the length is 2/5.
The linear ratio. That's what they gave you. It's important to talk about it in terms of that, just because this whole page is on linear ratios, area ratios, and volume ratios. So they just gave you the linear ratio. What's the volume ratio?
Would it be 16/20 or 125?
It's the numerator cubed over the denominator cubed. You got the 125 right, but 2 cubed is not 16. It's 8.
Oh.
2 times 2 times 2 is 8. That's what cubing means. 3 cubed is 3 times 3 times 3. That's 27. Okay?
Okay.
Now, that's probably why they use fractions, because all their problems, the numerator and the denominator is exactly the size integer that produces an integer when you do whatever you have to do to it.
Yeah.
So actually it's 6 o'clock. We can do this in 30 seconds. The ratio of the weights is what? what are they giving you with that?
The volume.
So volume ratio is 27 over 64. What's the ratio of the radii? What are they asking for? Regardless of what they're asking for, what's our first step here?
To find the linear.
What's the linear ratio?
3 over, what do we?
You know it's a small number and you know it's an integer. It's not a fraction. They don't give you fractions in these problems. At least not yet. It's either 2, 3, 4, or 5. You can almost always be certain.
Okay.
4 cubed. They grow fast when you cube a number. 4 cubed gets to 64 very quickly. Now, what are they asking for? We have the volume ratio. We have the linear ratio. We don't have the area ratio. What would the area ratio be, just in case they were asking for it?
9 over 16.
Which one are they asking about?
I think it's,
How do you measure radii?
I have no idea. I've never even heard that word before.
A radius. The radius of a circle.
Oh, okay.
What's that measured in?
That's the linear.
Okay. In other words, it's measured in inches or feet or meters, which means the linear ratio, that's the answer. Okay?
Okay.
It's really pretty straightforward, actually. As long as you just are aware that, as long as you know the linear, area, and volume, then you can pretty much answer any question they're going to ask you.
Okay.
For questions like 3, which are squirrely questions, but that's okay. I'm pretty sure we got the answer. It's just 7 times that, her eye distance, her eye length. Let me know if that's not the answer. I'd be curious.
Okay.
Then it's a much more complicated geometry problem, which is going to deal with similar triangles and all kinds of stuff, and angles and all of that. And I don't think they really intended you to do all of that with this problem. So, all right, Morgan, I will talk to you next time.
Okay. Thank you so much.
You're welcome. Bye-bye.